Okay, can you hear me?
Yes, sir.
Right, okay. I think you can see the screen now. Isn't it? Hello? Can you see the screen?
Yes, sir.
Right. Right. Today I'm going to start the new chapter. Actually it is called new chapter about vector spaces. Right? Later. Okay. So what do you know about vectors? What do you know about vectors? ඔගොල්ලෝ vectors කියන අහලා තියෙනවද? කාවිහල් පැට්‍රි කේලි පැට්‍රි කියනීලා. Vectors. So you know that, right? Okay. The one, you know that the vector means it has a direction and the displacement. Understand? The modulus value, isn't it? Right. So actually vectors, normally vectors we denote, say for example we say vector v is say I plus j, ne? Or vector u is equal to 2i minus 3j. These are called vectors, isn't it? Hello?
Hello, sir.
Right. So you know about the vectors about this, ne?
Yes, sir.
These type of vectors you studied. Normally we denote like this. This is something different. We are going same thing in a different mode. We are going to discuss about vectors here. I and j. So somewhere here 2i minus j, some like this, minus 3 and 2. So this is 2i minus j. This is I plus j, right? So in other term, we can denote this vector as 1, 1. That means I component is 1, j component is, yes, tell me.
1.
1.
Yeah, u can be written as the form of 2, minus 3. Okay.
Okay, sir.
So these are the not we denote the notation. If you denote this one, this is called. So in here there are 2 coordinates, no? So you should know about that. This is 2D space, 2-dimensional space vector, 2D space vector. I will come to vector space definition later. Right. Suppose if I have given 1, 0, 2. What is this vector?
3D space vector.
3D space vector. Suppose if I have given minus 1, 2, 3, 4. This is 4D vector. That means 4-dimensional. So similarly, we can go up to n-dimensional and as well as infinity, right? Okay. So these vectors we denote by this letter V, U, V under sometimes some books it's denoted that in the dark letters, no, block letters, bold අකුරු වලින් සමහර පොත්වල ලියලා තියෙනවානේ vectors වල. ඔයගලන්ට උසස් පෙළ විභාගෙත් bold අකුරු වලින් එන්නේ. ආවේ. Yes. Hello. Hello.
Hello, sir.
මේ ඔයගොල්ලෝ මේ මට රෙස්පොන්ස් කරොත් තමයි මට කන්ටිනියු කරගෙන යන්න පුළුවන්. So සමහර vectors underline කරනවා. සමහර books වල ඒක bold කරලා ලියලා තියෙනවා. சில புத்தகங்கள்ல அத போல்டா எழுதி இல்லாட்டி சில இதுல அந்த எழுத்துக்கு கீழ ஒரு கோட் அடிச்சி. Sorry, underscore. Okay. So these are called vectors. U, V, W. Or sometime I will write for easy U, V, W, small letters, right? So these, so if these collection, if we say type of vectors, if these collection have combining all these collection, collection, we called a new set. That is called a capital V. This is not a vector. This is capital V, right? The collection of vectors is denoted by capital letters. Capital S denotes some vectors, right? Vector X, Y, Z, etc. Right? So capital P denote Y1, Y2, Y3 as vectors. Right? So these vectors may be sometime y1 is the vector 0, 1, 1 or any type. y2 is 0, -1, 0. Maybe anything, but we denote this as small letters. These are called vectors. Whatever dimension, no problem. It is a dimension or matrices. No problem. We are denoting as a matrices here. Vectors. This is the collection. This is the set of vectors. P is called set of vectors, right? So R2. So R real set of real numbers, right? We can say that -3, -2, -1. Everything. Any real number. Say Z is set of integers, right? -3, -2, -1, 0, 1, 2, 3. It's going like. So set of integers. These are all elements. We can say this is also a vector. So 1D vector, one-dimensional vector. That is one-dimensional vector we denote by capital R. Capital R. So every vector in this set is U, V, W, which form. So every vector is denoted by U is denoted by something called A or something A, which is A is a real number, right? So if you say R2 vector, U, V, W, whatever. So U can be written as the form of A, B coordinates, where A, B is in R. A and B are real components, real numbers. U, so first component of U vector U is A, second component of B is B, right? So similarly R3. Say x1, x2, x3, etc. So say xi, ith x, whatever. Say This one is AI, BI, CI, where AI, BI, CI are components of real components. That is, these are called entries. These are called entries. Entries. So in this way, we can denote. So collection of vectors are called set of vectors. Set of vectors. These collections. So in these collection, this vector collection is so these are the collections of vectors. So inside these entries are components. So maybe it is a 3D or 4D or 5D or ND, whatever. Say R5, what will be there? Say I will denote Y1, Y2, Y3, right? What is YI? What will be YI? Tell me.
There are 5 entries in that.
Five entries. I will put AI,
BI,
BI, CI,
BI,
DI, ABCD, EI. So there are 5 entries should be there. It may be different. For example, say Y1, anything like Y1, 0, 0, 0, 1, 1. This is also one entry. Sorry, one vector. So such type of all entry, all type of collections included in R5, 5 entries collection. Actually, these are called vectors. So vectors we denote in hereafter in this form, right? So scalars we are denoting alpha, beta, gamma, like that, lambda, mu, like that we denote scalars, right? So alpha time u means what? This is a scalar product of sorry, that means vector u is multiplied by scalar. Understand? That means alpha time, say u is a comma b, just a vector a comma b, a b. Then we can multiply inside, no, alpha a, alpha b. This way we can multiply inside the vector, right? Is it okay?
Okay.
So this alpha, beta, gamma scalars are collection denoted by the set F, capital F. So in other term, we called a field. We will study in the next year what is field. This all scalars we are taking from the set capital F, which are denoted by alpha. These are actually real numbers. For the time being, you think that it is a real number. Maybe complex number as well, right? Okay.
Okay, sir.
Okay.
Understand? Right. Make a ඔයගොල්ලෝ හිතේ තියාගන්න මේ scalars කියන්නේ scalars කියන වර්ග දෙකයි ගන්න පුළුවන් ඇත්තටම මේ වෙලාවේ අපිට real numbers හෝ සංකීර්ණ සංඛ්‍යා, තාත්වික සංඛ්‍යා හෝ සංකීර්ණ සංඛ්‍යා, right? So okay, you think that this F means the real numbers or complex numbers. Okay, so scalars is different from the vector. You know how to differentiate those two. Understand? What is the difference between vector and scalar?
Vector has a direction and
Direction. Okay.
but scalar haven't a direction.
Scalar is just a number, just a value, right? Okay. Now, so 1 minute. Right. So now we will come. So you know that you have an idea about a vector and a scalar. Now you know that capital V. We denote normally in capital V, capital W, capital P, capital letters. If we denote by capital letters, we are called set of vectors. These are set of vectors. මේක ලියාගන්න note එක මම ආපහු මේ සමහරවිට note දෙන්නෙත් නැති වෙයි. Set of vectors. Set of vectors, huh? So these capital set of vectors denoted by capital letters. Sets of vectors, capital letters, right? So similarly, right. Vectors are denoted by small letters, right? Scalars are denoted by alpha, beta, gamma, lambda, etc. Right? Right. So set of scalars denoted by capital F. So for the time being, I will take capital S as R. That means set of real numbers. Mainly we are using these two. Or according to the situation, we will change set of complex numbers. Set of complex numbers, right? Right. Set of scalars denoted by F. F is mainly we are taking in this whole chapter F as R and O C. One of those two. Right. So the vector space means a vector space V, capital V. We say vector space capital V over the scalar F. Right. Vector space capital V or capital W or whatever. මේ space එකක් ගැන කතා කරන්න. මේ set එක අපි space එකක් වෙනවා නම්, if you want to say that this set of vector is a space over the field F, there are some conditions. There are some conditions to satisfied by these vectors, right? So I will write the perfect definition for this one. Right, a vector space V, over F. F means, that means ROC for the, in generally F we are denoting. So in here I am going to take ROC, right? Over F. එතකොට මෙතන scalar values උත් තියෙනවා, vectors උත් තියෙනවා. මේ එතකොට මේ collection of V කියන එක vector space එකක් වෙන්න නම් මේකට සමහර properties satisfy කරන්න ඕන. සමහර criteria satisfy කරන්න ඕන. Right? So a vector space V over F denotes V F right? The vector space V over F denotes V over F. So we denote right? A vector space V over F is non-empty set satisfying the following axioms or conditions. Following conditions. එතකොට if we have to say V is a V කියන්නේ මොකද්ද? Collection of sets. ඒකනේ? Understand?
Yes, sir.
V is a collection of set. F is a field. It contains all type of scalars. It may be a scalar කිව්වොත් ඒකේ ඒක scalar එක real numbers වෙන්නත් පුළුවන් complex numbers වෙනවා. මේ හැබැයි දෙකම කවල මේ තියන්න බෑ. complex numbers නම් complex numbers, real නම් real. හරිද? දැන් මේකේ වැදගත්ම දේ මේක non empty set එකක් වෙන. non empty කියන්නේ මේ කුලකයේ ශූන්‍ය වෙන්න බෑ. නේද? How to call it is non empty in Tamil? Any Tamil student here? Tamulaala என்ன சொல்றது non empty set? Nobody is there. So no problem. So in Sinhala, how to say that non empty set?
නිශූන්‍ය.
Okay. right. ඒ කියන්නේ ශූන්‍ය වෙන්නේ නැති එක. එතකොට අඩුම ගානේ එක අවයවයක් හරි ඒක ඇතුලේ තියෙන්න ඕනේ. අපි මේක කියන්නේ B should be non empty. එහෙම නේද? මෙහෙමනේ?
Yes, sir.
A vector space V over F denotes V over F is non empty set satisfying the following conditions. So these vectors and scalars together with this all together with should satisfy the following axioms, right? So vector addition, first vector addition in the first vector addition two pair of elements right? Vector addition. If U comma V are elements of V, what are the U and V? U and V are vectors we are taking from the set V, right? If U and V are in A, U and V are from V, they are correspond a unique element U plus V is in V. Right? So if you have take any two elements, right? So maybe you can put this as a first condition, right? Any two elements, U and V, that addition must be in that set. ඒක පැහැදිලිද? තේරුම් නැත්තම් කියන්න.
තේරුණා සර්.
ඒකේ අපි කියමුකෝ අවයවයන් දෙකක්. ඒ කියන්නේ වෙක්ටර්ස් දෙකක් ගත්තොත් ඒ දෙකේ එකතුව යුනික් එලිමන්ට් එකක්. යුනික් කියන්නේ ඒක දෙකක් වෙන්න බෑ. u + v කියලා දෙකක් තියන්න බෑ. එකම එක u + v එකක් තියන්න ඕන. ඒකත් ඒ සෙට් එක ඇතුළත තියෙන්නත් ඕන. තේරුණාද? මේ v කියන සෙට් එකේ u + v තියෙන්න ඕන. මම කියන්න කන්ඩිෂන්ස් ටික මේ වෙක්ටර් ස්පේස් වෙන්න ඕන කන්ඩිෂන්ස් ටික කියන්නේ. පළවෙනි කන්ඩිෂන් එක මොකද්ද? මේක if කියන වැඩිය let කියලා දාමු. Let u and v are in v, they are correspond unique element u + v is in v. හරිද? මේක තේරුණාද? This is just not a addition, this is a vector addition. What is called, sorry, vector addition. Is it clear? The second condition. So this is a very, very important part in linear algebra. As matrices, everything is depend on this. So carefully listen this. Right? Now let u and vr is in v. I will put this one as like this. Then u1 comma u2. That is better. u1 plus u2. Okay. Let us take u1 comma u2 is in v. Then u1 plus u2 must be equal to u2 plus u1. This is called commutative law. Commutative law. එතකොට මොකද්ද? මේක u1 එකයි u2 එකයි එකතු කරාම එන එක u2 එකයි u1 එකයි එකතු කරාම එන එකට සමාන වෙන්න ඕන. මේක පැති මාරු කරලා තියෙන්නේ. Understand? This is converted. This is commute. So convert into the other side. Right? So this is called commute. So let u1 and u2 are two vectors in v. Then u1 plus u2 must be equal to u2 plus u1. Okay. Right.
Okay, sir.
Third one. Let u1, u2, u3, three elements. Let us take three elements from v. If you take three elements from v, okay, three elements from v, then the next condition should be like this: u1 plus u2 plus u3 equals u1 plus u2 plus u3. මුලින් දෙකක් වෙක්ටර්ස් දෙකක් එකතු කරලා තුන්වෙනි එකත් එක්ක එකතු කරන එකයි මුල් එකයි දෙකයි තුනයි එකතු කරලා මුල් එකත් එක්ක එකතු කරන එකයි සම. So this is called associative law. This is called associative law. Right? Associate window. Right. So the fourth condition, we say that additive identity. There exists an element, say 0 element, 0 is in V such that for all U is in V, U plus 0, 0 U must be equal to U. Identity element, we denote this by 0. Additive identity, we denote by 0. That means vector 0. This is not just 0. This is a vector 0. That means I will put as 0 vector. This is 0 vector, right? There exists a 0 vector is in V. For if you take an addition with that 0 vector for any element in V, any element, not only the one, the particular number of elements. If you take any element and add with this, if you add the right or left, this is right addition, this is left addition, no problem. Output will be the same. U plus 0 or 0 plus U must be U. If so, the additive element is there. Additive element is there. That is the additive element must be there is a condition of the vector space. Is it clear?
Yes, sir.
Additive element, additive identity. The fifth condition, additive inverse. This is called additive inverse. Additive inverse. For every U1, every element U is in V, every element U is in V, there exists an unique element W is in V such that U plus W is equal to W plus U must be 0. 0 means this is 0 vector. This is identity, 0 vector. Additive identity. This is called additive inverse. So W is an inverse of U, U is an inverse of W, vice versa. Harida, U plus W or U is a additive inverse of V. W is an additive inverse of U. Harida. Right. So how many properties I have given in addition? Vector addition?
5 properties.
5 properties. What is the first one? Tell me.
U1, U2 related to the V, there are corresponding and unique element. U1 plus UV related to the V.
Right. That's correct. If you take any two element, U1, U2 කියලා දෙකක් ගත්ත ඕනෑම අවයවයෙන් දෙකක් ගත්තොත් ඒකේ එකතුව එක යුනික් එලිමන්ට් එකක් වෙන්න ඕන. ඒකේ එකතුව ඒ සෙට් එකේ තියෙන්න ඕන. Understand? It should be inside the set. That is the first condition. The second condition is what?
If we add 2 vectors and we change the position of that vectors, then add that vectors are equal to the first one.
Right. That means commutative. Shortly, you remember that commutative. If you take any two vectors, you and take the addition, vector addition U plus V, which is equal to V plus U. Okay, that is called a commutative law. What is the third one?
Associative law.
So if you take any three element u1 u2 3 u3 කියලා ඕනෑම elements තුනක් ගන්නවා ඕනෑම elements තුනක් ගත්තොත් if u1 plus u2 plus u3 is equal to u1 plus u2 plus u3 ඒ කියන්නේ ඉස්සලා දෙකක් එකතු කරලා තුන්වෙනි එකත් එක්ක එකතු කරන එකයි ඉස්සෙල් එක තියාගෙන 2යි 3යි එකතු කරලා පළවෙනි එකත් එක්ක එකතු කරන එක සමාන වෙනවා. This is called associative law. This is called associative law. Understand? What is the fourth one?
Every vector plus zero vector or zero vector plus every vector equal to the every vector.
Zero vector means identity, yeah, not zero. You don't use the term zero vector. What I put here, identity. If you add any element with an identity, that will give so if you add right or left side with identity, that will give the same vector itself. That is equal to same vector itself, right? Okay, the fifth one is what?
If we add two vectors, then addition of two vectors are equal to the zero vector. And then first one is additive inverse of second one, or second one is additive inverse of first one.
Vice versa, right? So every element, this is the term used for every element in V, set V, must have a additive inverse. For every element V, there exists an element W. ඒ කියන්නේ හැම එලිමන්ට් එකකටම තව එකක් තියෙන්න ඕන පෙයාර් කරන්න පුළුවන්. ඒ පෙයාර් එකත් එක්ක ඇඩ් කරොත් එන්නේ අපිට ඩෙන්සිටි වෙක්ටර් එක. Is it okay?
Okay, sir.
Right, that is clear. So up to now we saw that vector addition. That is for these 5 conditions must be satisfied for vector space. There are some more conditions. Scalar multiplication. Right. Right. In here, the first condition, for every u is in V, every element u in the set V, right? And for every element u is in V, and any alpha is in F. දැන් තමයි මේ ස්කේලර් එක එන්නේ. ඕනෑම වෙක්ටර් එකයි any ඕනෑම ස්කේලර් එකයි අරගත්තොත් dot product එක there exists a corresponding corresponding unique element alpha time u should be in V. මම හිතන්නේ මේක පැහැදිලි ඇති. ඕනෑම වෙක්ටර් එකක් ගත්තොත් ඕනෑම ස්කේලර්ත් එක්ක ඒක ස්කේලර් මල්ටිප්ලිකේට් කරොත් ස්කේලර් මම මේ ඩොට් එක මෙහෙම දැම්මා ස්කේලර් මල්ටිප්ලිකේෂන් කියලා පෙන්නන්නේ මම මෙහෙම ඩොට් එක දාන්න. that is better. මේක වෙක්ටර් ඇඩිෂන් නේ. මම මේකට මෙහෙම දාන්න. මේක නිකන් ඇඩිෂන් නෙවෙයි වෙක්ටර් ඇඩිෂන් නේ. I will put like this. This is vector addition. Right. So now you can think it of, right? So this is not a normal addition, vector addition, right? In here, scalar multiplication. Alpha කියන එක value එකක්, u කියන එක vector එකක්. ඒකත් එක්ක scalar multiplication එකක් ගන්නවා. ගත්තොත් ඒ scalar multiplication is the මේක vector එකක්ද? alpha time u කියන්නේ vector එකක්ද?
Yes, sir.
Right, definitely. ඕනෑම vector එකක් scalar එකෙන් multiply කරාම අපිට හම්බෙන්නේ vector එකක්. එතකොට alpha u කියන එක අනිවාර්යයෙන්ම vector space එකක් වෙන්න නම් alpha u කියන එක ඕනෑම alphaත් එක්ක වැඩි කරලා එද්දි ඒකෙන්ම තියෙන්න ඕන කියලා මෙයා කියනවා. Understand?
Yes, sir.
Right. The second condition in scalar multiplication, right? Alpha time beta time u, right? Alpha time beta time u is alpha beta time u, right? For every u is in V and alpha comma beta is in F. මේක පොඩ්ඩක් පැහැදිලි කරන්න මට. So can you please explain this one? Anybody can explain? So for every alpha comma beta is from F. ඕනෑම ස්කේලර් දෙකක් ගන්නවා. ඕනෑම වෙක්ටර් එකක් ගන්නවා UV වලින්. ඕනෑම ස්කේලර් දෙකක් F වලින් ගන්නවා. ඕනෑම වෙක්ටර් එකක් ගන්නවා වෙක්ටර් U කියලා වෙක්ටර් එකක් ගන්නවා V වලින්. ඒකත් එක්ක alpha.beta.u is equal to alpha.beta.u. Okay?
Okay, sir.
Right. So hello.
Hello, sir.
Right. Okay. Right. Next is multiplicative identity. Right. 1 into, we denote 1, 1 or E. Some books it denoted as E. 1 into U is equal to U for every U is in F, sorry, U is in V and 1 is in F. This is called scalar multiplicative identity. Scalar identity. Scalar identity. Right? Scalar identity. So for 1 is in 1 කියලා element එකක් තියෙනවා. For right? For every U is in is, and this is not and, where it is better. Where 1 is in, right? Where 1 is in F. Right, that is scalar. How many properties in scalar multiplication?
3 properties.
3. Altogether now how much?
8.
5 plus 3, 8 properties we have, right? So now next is the distributive law. Distributive law. Right. Distributive law, right? For every for any alpha beta in F and UV for any alpha comma beta is in F and U comma B is in B, the following holds. The following properties holds. මේ ඕනෑම alpha beta කියන scalar එකටයි u, v කියන ඕනෑම element එකටයි මේ කියන මේ laws ටික holds වෙනවා. Right? Alpha scalar product u plus v, right, equal to alpha dot u plus alpha dot v. The second property in that one, alpha plus beta dot u is equal to alpha dot u plus beta dot v. Alpha dot u plus beta dot sorry, it should be what?
U.
Yes,
beta dot u.
Beta dot u. Right, these are called scalar so distributive property. So if those 10 properties, how many properties?
10.
10 properties. If these 10 properties are wholes, right? If these 10 properties are wholes, what we say? V is a vector space over F, right? V is a vector space. එකනේ දීලා තියෙන්නේ. මේක vector space වෙන්න නම් පල්ලෙහා තියෙන properties ටික hold කරන්න ඕන. එතකොට how many properties?
10 properties.
Right. Right. Then what do you say that the elements of F are called?
Scalars and complex numbers.
No. Just scalars. Scalars වල scalar එක complex number එකක් වෙන්න පුළුවන්, real number එකක් වෙන්න පුළුවන්. Scalars, just no, forget about real and complex, no worry. Okay. The elements of F are called scalars. Elements of V are called
Vectors.
Vectors. Right. Okay. Right. So in note, shall we write as a note this one? Note. Right. First one. Elements of F are called what? Scalars. Hello? lecture on the pro page mo. lecture on la page mo. Elements of F are called scalars. Elements of V are called what?
Vectors.
Vectors. Right? Elements of called vectors. We did not zero as zero element in F and zero actually bold zero, zero as zero vector in V. Hello lecture right. We denote just zero as a zero element of in F and zero as zero vector in that means bold zero in V. ඒක පැහැදිලිද?
Yes, sir.
Right. If V is a vector space over R means real numbers, instead of so F in here F is equal to R, I have take. That means R means set of real numbers. If V is a vector space over R, then V is called real vector space. V is called real vector space. Right? Real vector space. 5. If V is a vector space over, what is this notation? C. Complex numbers. C. Set of complex numbers, then V is called complex vector space. Right? Right. right? මේක තේරුණාද? Right. We will see the example of the vector space. Example of the vector space. Oh. Screen එක පේනවද?
Also.
All right. Now example. P is given that A comma B such that A comma B is in R, right? A comma B is in R. A and B are component, real components, right? Show that V is a vector space over R over F, which is equal to R. එතකොට මෙතන ස්කේලර් එක දීලා තියෙනවා real numbers කියලා. මේක පෙන්නන්නලු. මේක vector space එකක් කියලා පෙන්නන්නලු. ඒක කොහොමද පෙන්නන්නේ දැන්? එතකොට මේ 10 properties ඔක්කොම පෙන්නන්න ඕන. කොහොමද පෙන්නන්නේ? Solution. One by one කියන first condition එක මොකද්ද වෙන්න ඕන? ඕනෑම element, if you take any two elements from V, that addition must be in there. Understand?
Yes, sir.
Right. So first property, let A1 comma B1 comma A2 comma B2. හරිද? මම elements දෙකක් ගත්ත හරිද? Right. So then take the scalar addition. Sorry, vector addition. Vector addition එක add කරන්නේ component wise නේද? මේක මේ ඇතුලේ components wise නේ add කරන්න ඕනේ. So we have to add like this. Just this is a normal addition. Normal addition, A2 plus B2. Is that okay? හරිද? First component is added with second component. First component of the second element. Second component of the first element is added to the second component of the second element. Is it correct?
No, sir. We have to add by corresponding elements, right?
Yeah, I have add corresponding element now. A1 plus, oh, sorry. Thank you. Yes. A1 plus A2, B1 plus B2. This is wrong, Now correct. So now tell me, this after addition, is this an element of V?
Yes, sir.
Is this an element of V? මේ element එක V වල තියනවද? ඇයි හේතුව තියෙන්න? Why the reason is why it should be there? What is the reason?
Because A and B are related to the
A1 plus A2 is a real number and B1 plus B2 also a real number. In here condition is, in the set condition is, the set A comma B such that A is from real number, B is all second component, first component is from real number as well as the second component is also from a real number. හරි නේද? එතකොට A1 plus A2 means A1 is a real number, A2 is a real number, A1 plus A2 also a real number. Is it okay?
yes, sir.
Similarly, B1 plus B2 is a real number. Okay? What is the next property? Check the next property. For next property, what you have to take? One by one. Huh?
Commutative.
Commutativity. So that let us take. මම මෙතන කෙලින්ම මේක v වල තියෙනවා කියලා දාලා තිනවා. First property is satisfied. First property satisfied. Satisfied. Okay. Now let a1 comma b1, a2 comma b2 is in b. Consider a1 comma b1 plus a2 comma b2 is equal to what? A1 plus a2 comma b1 plus b2. Is it okay? Right. How can we say that this is commutative? So it should be equal to what?
A2 plus A1 and B2 plus.
We can write this one. So this is since this is a real number, A2 plus A1, B2 plus B1. Then make a කොහොමද? A2 comma B2 plus A1 comma B1. So is that commutative now?
Yes, sir.
Commutative holds. Commutative holds. What is the next property? For that, what we have to do? How many elements we have to take?
3 elements.
3 elements. Let us take A1, B1, A2, B2, A3, B3. Okay. Is from V. B. Now consider. First A1 comma B1 plus A2 comma B2. Right. ඉස්සෙල්ලාම මේ දෙක එකතු කරනවා. පළවෙනි දෙක. එකතු කරාම මොකද වෙන්නේ? A1 plus A2 comma B1 plus B2 plus A3 comma B3. මේක හරිනේ. දැන් මේක ප්‍රසාරණය කරොත් A1 plus A2 plus
A3.
A3 comma B1 plus B2 plus B3. දැන් කොහොමද මේක associative ද කියලා ලියන්නේ? බලන්න. අපිට මේක මෙහෙම කඩන්න පුළුවන්ද? A1 comma B1 plus A2 plus A3 comma B2 plus B3. Is that same?
Yes, it is same.
Okay. Now A1 comma B1 scalar plus. So how can I break this one?
A2, B2. Like
A2 B2 addition. A3. Now tell me, is that associative?
yes.
Yes, ne? Right. 1 minute, I'll switch on the lights and come. Asha! මේ ලයිට්ස් ටික දාන්නකො. දැන් කීයද දන්නේ? වයින්නවද? නේද? මමත් එන්නේ නේද? මේ ලයිට් ටික දාන්නකො. අර එහා පැත්තේ දාලා තියන්න. එළියට දාන්න. Okay, is that associative? Huh? Associative holes. Associative holes. Clear? Right. What is the next property? එතකොට අපිට vector addition එකේ මේ අදාළ vector එකට මේ properties තුනක් satisfy වෙනවා. දැන් fourth property එක මොකද්ද?
Additive inverse. Sorry, additive
right.
inverse.
Additive
Identity.
identity. What will be the additive identity for this one? මොනව එකතු කරොත්ද මේක අර එලිමන්ට් එකම හම්බෙන්නේ?
Two dimensional zero vector.
Zero vector.
Zero vector. Zero vector is 0, 0. Let a comma b be any element v and 0, 0 is a zero vector. So if you add this one, a plus a comma b plus 0, 0, what will be the answer? A plus 0,
B plus C.
b plus 0. Inside this one, this is scalars, so no problem. A comma b. So what about 0, 0? One side is enough. I am checking the other side. So හරිද? එතකොට additive identity exists. Additive identity එකක් තියෙනවා. Identity exists, right? Right. What is
මොකද කරන්නේ? වහිනවද? අපිටත් වහිනවා.
හරි අපිටත් වහිනවා මේකත් පොඩ්ඩක් අහගමු මේ අපිටත් වහිනවා මිහින්තලෙට right උදේ ඉඳලම වැස්ස okay what will be the next property?
Additive inverse.
Additive inverse. So let a comma b in v, any element a comma b, then there exists minus a comma minus b in v such that a comma b plus minus a minus b. What will happen this one? මේ දෙක එකතු කරොත් a plus minus a b plus minus b. So what will get?
0, 0.
Zero vector.
0, 0. So therefore additive inverse exists, ne? commutative inverse exists. Is it clear? So first 5 properties, okay. What is the next 5 properties? Scalar multiplication properties. Scalar multiplication. First property, what is the first property? First property, scalars are taking from what? In here, what is the scale I have given in the definition? Scalar,
Real numbers.
real numbers. Now we are coming to the scalar multiplication. What is the first property? Let alpha be any real number. That is R, right? Alpha be any real number. A comma B be any vector. Right? Then alpha time A comma B is what? Alpha A, alpha B. Alpha A is a real, is that a real number? Make a real number ekadda?
No.
Alpha B කියන එක real number එකක්ද? ඔව්නේ. එතකොට මේ set එක B වල තියෙනවද? alpha A, alpha B කියන එක. According to the definition of V. V එකේ definition එක කියනවා V is contains A, B such that A is from R, B is from R.
Yes, sir.
තියෙනව නේද?
Yes, sir.
You are mathematics students, you should be careful about this. Alpha A into alpha B, because alpha is a real number, right? So therefore closure property holds. So therefore alpha time A comma B is in B, right? What is the next property? Let alpha is in R and A1 comma B1 comma A2 comma B2 is in from B. Okay. පැහැදිලිද? Then what should you check? ඔගොල්ලෝ මොනවද check කරන්න ඕනේ මෙතන? ඊළඟ property එකේ. Alpha dot time A1 comma B1 plus A2 comma B2. Okay. So alpha dot time. What will be the addition here?
A1 plus A2.
A1 plus A2 comma
B1.
B1 plus B2. Now, so if now I have to multiply inside alpha time A1 plus A2 alpha time B1 plus B2.
So
Okay.
excuse me.
Tell me.
So for my clarification, this is distributive law, right?
No.
This is
Oh, sorry. I am in the distribution law. I forgot it. So anyhow, we are coming to that now. Oh yeah. This one. So what is very good. You anyhow this property is coming, but anyhow we have to go for order. Order එකට යමු. Order එකට තමයි යන්නේ. Right. So let alpha comma beta is from R and
so we have we need two scalars in the vector.
now okay.
Yes, sir.
Now okay.
Yes, sir.
I have taken two scalars and this vector. checking that into beta dot product A comma B. So what will happen to this? Beta A plus beta B. Okay. Now what will happen? Alpha beta A, alpha beta B. Right? So further, alpha beta time A, alpha beta time A, comma alpha beta time B. So alpha beta I can take out, ne? Alpha beta dot product A comma B. Is that correct now? So first scalar multiplication property holds. So this dot is the multiplication between the scalars. This dot is multiplication between the scalar and vector. මේකයි අතර වෙනසක් තියෙනවා. මේකයි අතර වෙනස. නිකන් අර රවුමක් දාලා තියෙන එක ස්කේලර් එකත් එක්ක වෙක්ටර් එක මල්ටිප්ලයි කරන එක. නිකන් ඩොට් එක ස්කේලර් එකත් එක්ක ස්කේලර් එක මල්ටිප්ලයි කරන. මේ ස්කේලර්ස් දෙකක් නේ මෙතන. Right. Alpha beta. Right. That property holds. What is the third property? What is the third property? Please tell me.
Scale identity.
Scale identity. Scale identity is what? One, no? One is in R. That's right. For any A comma B is in V, such that one scalar multiplication into AB is equal to 1 into A, 1 into B. This is A comma B. Therefore, scale identity holds. That's right. So what is the third, what is the distributive law now? Distributive law. Now we are coming to that property. Let alpha is in R and A1 comma B1 comma A2 comma B2 is from V. A1 comma B1 comma A2 comma B2 is from V. Okay. Now check the property. Please check. Now consider alpha dot product A1 comma B1 plus A2 comma B2 A1 plus A2 1 plus B2. Right. So okay, so alpha A1, alpha A2, comma alpha B1, alpha B2. How to expand this one now? Is it possible to expand it alpha A1 comma alpha B1 here plus vector addition? This is vector addition. Alpha A2, sorry, alpha B2. So I can take out alpha from here. Alpha A2 comma B2. Harida. So distributive Where is the eraser? Right. So this distributive property hold. Is it okay? Yes?
Yes, sir.
Right. Okay. What is the next distributive law? Let alpha comma beta is from R and A comma B is from V. Consider just scalar addition into A comma B. So what will be this? Alpha plus beta into A, alpha plus beta into B. So this can be written as alpha A plus beta A, alpha B plus beta B. So I can separate this as alpha A comma alpha B, beta A comma beta B. So alpha can take out A comma B, beta can take out A comma B. Okay. So this distributive property hold. How many all properties are? So every properties, all 10 properties is all 10 properties are hold.
Yes, sir.
So therefore every property is of vector space holds for above set V. Therefore V is a vector space over R, or V is a vector space over R. මේක පැහැදිලිද? Right?
Okay, sir.
Right. This is clear. Right, I will give problems in this. Right, there is a nice theorem. So small theorem. Let V be a vector space over F. Then U plus V is equal to U implies V is equal to Z. V is equal to 0 vector. 0 for every U comma V is in V. Given that U and V are vector spaces. Is it clear?
Yes, sir.
Right. The second one, in the same theorem, there are three conditions. U. Alpha scalar product U, if and only if U is equal to 0, if and only if either u is 0, u is a 0 vector, or scalar alpha is equal to 0. May 0 එකයි may 0 එකයි වෙනස මොකද්ද? U is equal to 0 and alpha is equal to 0. What is the difference?
Is a zero vector, then alpha is a scalar.
Right. So the third one, the third part, minus 1 into scalar product of u. So u is in V and alpha is in F. So minus u for every u is in V. For every u is in V. පැහැදිලිද? එතකොට පළවෙනි මේ තියරම් එකේ කියන්නේ මොකක්ද? අපිට දීලා තියෙන්නේ V කියන එක වෙක්ටර් ස්පේස් කියලා. පැහැදිලිද? right. V කියන එක වෙක්ටර් ස්පේස් එකක් නම් මොනවද වෙන්නේ? අර වෙක්ටර් ස්පේස් එකක් කියපු ගමන්ම අර ප්‍රොපර්ටිස් 10ම අපිට ප්‍රොපර්ටිස් 10ම සැටිස් වෙනවා, හෝල් වෙනවා. හරිද? අර ප්‍රොපර්ටිස් 10ම ඔළුවේ තියාගන්න ඕන. මේ V කියන එක වෙක්ටර් ස්පේස් එකක් නම් මේ තුන කන්ඩිෂන්ස් තුනම ඉම්ප්ලයි වෙනවලු. මේක තියරම් එකක්. තේරුණාද? V කියන එක වෙක්ටර් ස්පේස් over F නම් මේ කන්ඩිෂන් එක හෝල්ස් වෙනවලු. wait just ඉවරද? දැන්ද සර් මම පොඩක් කලින් ආවද ලෙක්චර් එක? right. Okay. Hello.
Hello, sir.
Right. Now we will see how to prove. If V is a vector space over the field F, then all the above properties satisfied. Now we will see the proof. Okay, right. Now, how to prove this one? First proof. Since V is a vector space, since V is a vector space, right? Since V is a vector space, for every U is in V, there exists an element minus U is in V such that minus U plus U, which is equal to 0 vector. Is it correct? By which property? By which property?
Additive inverse.
Additive.
Inverse.
That means additive inverse. Existence of additive inverse here. මේ කාරණාව ඒකනේ. මේ by additive inverse. හරි නේද? Right. Now by using associative law of vector space, minus U plus V for U comma V is in V. Can we sorry for U comma V is in V, U comma V is in V, minus U plus V. Minus U is also an element of V. Keep it in mind. Associative law එකෙන් මේක කොහොමද ලියන්න පුළුවන් අපිට?
Minus U plus U.
Also minus U, also V in V. Because of already in here, right? So minus U plus V. So what is this? 0, no? 0 plus V. 0 plus V. Right. So this is equal to V by identity property. By identity property. Right. Keep it that one in your mind. Right? Oh, what I have to prove is right. No, this is not effective. Minus U plus V. By hypothesis given that what? If U plus V is equal to U implies V is equal to 0, no? Since this is U plus V, we can put U plus V. This is minus U plus U plus Is it clear? See, instead of u plus v, I have put u. This is given. මේක දීලානේ තියෙන්නේ. දීලා නේද තියෙන්නේ? මේ hypothesis එකේ දීලා තියෙන්නේ. u plus v is equal to u implies v is equal to 0. Okay. So I am taking that minus u plus v. So instead of u plus v, I have put this one. So what is this? This is equal to 0. Okay. ඒක පැහැදිලිද? 0 vector. මේක පැහැදිලිද? Is it okay? Hello?
Oh, sir. Yeah.
Right. So now the left hand side, take this as a 1. So minus u plus v, by associative law, I will write like this. By associativity. What is this? This is 0 vector plus v. 0 vector plus v. This is vector addition. Right? Right. This is equal to v. This is 2. 1 and 2 are equal by left hand side. Ne? 1, since 1 is equal to 2, implies v is equal to 0. Here another. Is it correct? That proof is okay? Okay. Right. The part 2, the second one, second proof. Second proof. We know that as 0 is a 0 vector, 0 is in V, 0 is equal to 0 plus 0. Is it okay? Zero plus 0. Okay. So now let alpha is in F, then consider alpha dot time 0. So this can be written as alpha dot time 0 plus 0. This is by 1. By 1. Then alpha dot time 0 plus alpha dot time 0. Right? So right, by the first part say u plus v is equal to u means implies v is equal to 0. Similarly in here. Okay. By first part, we can say that alpha dot 0 is equal to 0 because of in here, because of this, by the equation number 2. By equation number 2. alpha dot 0 is 0. For any alpha is in F. What we have to prove is for any alpha is in F. Right. Right. Next is, wait, still not finished. Alpha dot 0 is 0. Next is similarly 0 time u is equal to 0 plus scalars plus 0 u for any u is in V. For any u is in V, we can separate this one to u. Sorry. In here dot u plus u. I am taking the dot scalar 0 and with dot product u. Scalar 0 with dot product u. Similarly, now this implies by part 1 implies that 0 time scalar product u is 0. So take this as equation 3 and this as equation 4. There are two conclusions come, right? Two conclusions come. The right. There are two conclusions come. Right. Now we have to show that now suppose alpha dot u is 0. If alpha is 0, proof is over. Is 0, proof finish. Proof is over. If alpha non-zero, what will happen? If alpha non-zero, so alpha is non-zero, definitely alpha inverse exist. Alpha inverse exist. Then alpha inverse exist. Then alpha into alpha inverse is 1. Right? Alpha inverse means in scalar. Alpha is in F means alpha inverse also in F. So alpha into alpha inverse is 1. This is the identity of the scalar. Right? Identity of the scalar. Right? Identity of the field F. Right? So if alpha is 0, then this proof is over. So that is given in the part 2. That is given in the part 2. So we have proved that if this is 0, if and only if either u is 0, if alpha is 0. Now we come to alpha dot 0 is u. Alpha dot u is 0. So in this case, alpha 0 means proof is over. If alpha not 0, we have to show that u is 0. Then alpha or either u is 0. Right? Alpha is 0. From this one, proof is over. If alpha becomes 0, in here we prove that 0 dot u is 0. If alpha not equal to 0, what will happen? That is the question, right? Alpha not equal to 0. 0 vector is equal to alpha inverse. It is a scalar, any scalar into 0. We can write like this. We can write like this, right? Right. So again, instead of 0, I can put alpha dot u. Instead of this 0, I can put alpha dot u. So these two are scalars, distributive law. Therefore, alpha into alpha dot u by distributive law. Distributive law. Alpha into alpha inverse is 1, identity 1, which is u. This is nothing but alpha into alpha inverse is 1. Which property I have used? Property of vector space. Right. So this becomes u. This is scalar identity. So that implies that vector u is 0. So if either alpha is 0 or u is 0, this is the proof. So the second part is, as 0 is in V, 0 is equal to 0 plus 0. 0 plus 0, we can put for now, let us take alpha is in V, consider alpha dot 0. Alpha dot 0, we can put instead of 0 by 1, 0 plus 0. Alpha dot 0, so if you, this one. So by part 1, definitely this is 0, but in the proof of the part 1, we have proved this one. So next is similarly 0 into dot u is u plus u, then that is also u. So because 0 is a 0 also, just 0. This is not a vector 0. 0 is an element of V. So since alpha is alpha dot 0 is 0 and 0 dot u is also 0. Suppose alpha dot u is 0 in the hypothesis given in the second part. If alpha is 0, by 4 proof is over. By 4 proof is over. Alpha is 0 by 4. This is say 5. 4 comma 5 proof is over. 4 comma 5 proof is over. If alpha non-zero, we have to show that u must be 0. So that will be, so if alpha is non-zero, in the scalar property, we know that every non-zero element, real numbers or complex number, have an inverse. Ne? So if you say 2 into half is 1. So 2 is an inverse of half, half is an inverse of 2. So alpha inverse must be exist if alpha is non-zero. 0 means 1 over 0, no. So it will be in trouble. So if alpha is non-zero, alpha inverse exists. Alpha into alpha inverse become the identity. Right? Identity. So 0 vector is equal to, I can write this one. So any alpha, no. So alpha inverse also a scalar. Right. So I am consider again alpha for instead of 0, I can put by something 5. By 5. By 5, I can put alpha dot u. So I will take out these two scalars and alpha inverse into alpha dot u, and which is 1 dot u, it is equal to u. Then which becomes 0. The third part, right, third part as 0 is equal to 0 vector is equal to 0 dot u, 0 dot u, 0 dot u, 0 dot product u. Instead of 1, I can put 1 plus minus 1 into u, right? Therefore, I can write this one u plus minus 1 into u plus minus 1 into u, right? Right. Now this one is u plus minus 1 into u is 0. By part 1, here see that by part 1, yeah, by part 1 minus 1 u is equal to minus u, right? Right, okay.
So excuse me.
Yeah, tell me.
So the mail layer konja solleluma number 3 nu potu line.
Right. 0 is equal to, I have taken that 0 into scalar product u. So instead of 0, I put 1 minus 1. Is it okay? 1 minus 1.
Okay,
Right.
so -1, okay.
So then I have multiplied this one. So this is the scalar multiplication. U plus minus 1 into u. U plus minus 1 into u is u. Minus 1 is u. Right? Right. Okay.
Okay, sir.
Right. So I will, so is that minus u in one another term? Minus u also is in V. Is it correct? Minus u also in V. Is it correct?
Yes, sir.
Yeah. I am going to add minus u both side in this one. So this is, take this as equation 6 or something. Add minus u both side. 0 plus minus u. Okay, right. So associative law, u plus minus 1 into, this is u. This is minus u. Okay, add after adding, right? So this becomes 0. This because identity property. So inverse property, additive inverse property, minus 1 into u. This is minus u. In here also identity property used. So this one minus 1 into u is equal to minus. Okay, right. Okay, that's the thing of vector space. Another example I will give. V is equal to A, B, C, D is a 2 by 2 matrix where A, B, C, D are real numbers and AD minus BC, that means determinant, no? Determinant is equal to 1. So the set containing the 2 by 2 matrices, the set containing 2 by 2 matrices, which A, B, C, D, such that A, B, C, D are real numbers and the determinant of the every vector in the set V is equal to 1. Determinant of every vector in the set is 1. Show that V is vector space over R. Show that V is vector space over R. Do it at home, this one. Okay? Do it at home. Is it clear?
Okay, sir.
Right. I will give problems as well. And next class I am going to take day after tomorrow, Thursday. Okay. Shall I take the class around 6 o'clock?
Okay, sir.
Okay, as 6 or 7, I will send an invitation tomorrow. Day after tomorrow. So hereafter, now I came to university from home. So because morning hours I am working because of this A-level paper marking is going. I am the chief of that. So I have to work. I have a lot of work there. So morning onwards, I am working for that. So I will take continuously every other days. Thursday, you will be having a lecture at 6 or 6:30. Yeah. I will send an invitation for Thursday night. You will be having lectures. Shall I stop now?
Okay, sir.
So you do it this problem and
So excuse me.
yes, tell me. Tell me. Yeah, please tell. Yeah, hello.
Sir, by Thursday, on Thursday mean 6:30 my vecha konjam nalla milla suggestion undu sir, because the maghrib kalawa idundu aithan.
Okay, no problem. 6:30. No, I will send an invitation. Anyhow, I have to check the time and I will send you sometime. It will be a 7 o'clock or 8. Okay, no problem. You are attending from home, no problem, no. So I will take the lecture. Okay, I will send an invitation tomorrow because I have to take continuous lectures because in here easy to take lectures than home. From I have to take the lectures from the university because all the facilities are here. No, from my home it is very difficult to conduct lectures. So I can continuously take and finish it off. So I try to take the next lecture day after tomorrow and we'll see. Okay, I will send the invitation tomorrow. Okay, bye.
Okay, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay, bye.